Welcome to the fifth video clip in this series, LED luminaires, light planes. Specifically in this clip, we're going to begin the introduction to light-emitting diode strips, a particular format that you can purchase LEDs surface-mounted to 5-meter strips for easy mounting in your luminaire light fixtures. If you look closely at this slide, the LED strips there that are curled up, they come in 5-meter strips in plastic reels that you can see 4 colors here. Now these are all monochrome LED strips. All of them that you see here, all the LEDs on the whole strip are all one color. They're either white, warm white, cool white, blue, orange, green, red, yellow, violet, magenta, whatever. These are monochrome. We're going to work almost exclusively with RGB LED strips. I want you to notice, though, that each square there, look at the orange one, there are 3 LEDs mounted inside that device. And you can see the 3 dots, the 3 orange dots. Now, the RGBs that we're going to use, the ones that I prefer, have a red, a green, and a blue LED in that little square device. So each one of these are all the same wavelength of color. There are dozens of unique colors that these can be purchased in. Now we're going to work strictly with red, green, and blue for this first run of projects. I have done some luminaires where I used multiple strips. One strip all red, one all green, and one all blue, mounted them right next to each other, then controlled the strips individually to get all the different colors. Later we hope to add schemes of using other LEDs outside the basic colors. However, if you don't stay focused on one approach and just go wandering around on the web looking at products, you might get confused. One of the factors when purchasing LED strips is the length. We're just going to assume that you're going to purchase yours in 5-meter lengths. That's the most common, and because of the surplus of these 5-meter strips, they're very inexpensive, anywhere from $10 to $20 on eBay for a 5-meter strip. Now there are other considerations that you have to make, so don't pause and run, go to eBay and start buying these strips, these LED strips. Watch to the end of at least all of the information on the LEDs, and we actually get into construction of the white holes, the white boxes, the white holes as I call them, before you go run off and buy in LEDs. First consideration is the distribution of the LEDs on the strip, particularly the distribution of color. And I have used 2 different formats, and it is a good idea to consider each of these distribution points separately. There are 2 strips that I have used in my light planes, and you see them right here. The 2 images are not to the same scale because I wanted to illustrate the color, not the actual physical distribution compared one strip to the other. The top strip has alternating red, green, blue, or as you see it, red, blue, green for the entire length of the strip. Whereas the bottom strip has a red, green, and blue LED within each device. If you look closely at the devices on the bottom strip, you will see a green dot to the left, a blue dot to the right, and a red dot between and above those 2. I have turned the drivers all the way down to the lowest level just to get my camera to pick up the colors. What the camera sees and what the eye sees are 2 different things. To demonstrate the results with these devices in aperture diffusers, I built some frames out of dimensional lumber to illustrate some points. But before we jump to the next slide, notice that the blue LED on the bottom set there, and even on the top set. On the top set, it's easier to see what's blue and what's green. I mean, red is obvious, but the green and the blue aren't. Well, the green's pretty obvious, but the blue tends to wash out or to overdrive the CCD in the camera. the charge coupled device that actually captures the image. So it tends to saturate those few pixels that are picking up the blue. If you look down on the bottom, the blue LED looks real bright, and it has overdriven the CCD in the camera. Another thing I want to point out is on that upper strip. You see on the left end it says plus BGR, blue, green, red. When you look at the LED, you see a blue one, then an R, DC 12 volts, red one, G. Well, the R is for the next one down the trail. So you leave the blue, the next is R. You leave the red, the next is G, green. You leave the green, the next is B, blue. If you didn't have the LED strip illuminated, energized, powered up, you might not realize which one of these devices on the top strip is red, which one's blue, and which one's green. Now on the bottom it doesn't matter, because the point of origin of light from the LEDs in the top strip are spaced apart by some fraction of an inch. In the bottom strip, the point of origin for the red, green, the blue are, for all intents and purposes, in the exact same spot. I mean, they're only separated by a couple thousandths of an inch. The upper strip presents a challenge that the bottom one doesn't. I prefer to strictly work with the bottom style of strip. Okay, so we built some frames out of dimensional lumber. This is a diffuser, an aperture diffuser laying on top of an LED strip that has some red and blue energized, so you can see it's kind of magenta. But what you're looking at here is a 24-inch by 24-inch or 2-foot by 2-foot sheet of 3/8-inch plywood painted matte white, and then a strip of 5050. I call it 50/50, but that doesn't mean 50%, 50%. So when you say 50/50, that has to do with the dimensions of the device. Anyway, I have a strip of 50/50 RGB LEDs, and then I have a 24-inch by 24-inch aperture diffuser that's using a vinyl sheet that I described before, sold as a drop cloth. And basically, and I show you how to do this in a later slide, you lay your wood frame down on the vinyl material, and then in a middle point on each side of the wood frame and on the vinyl you put some contact cement. And then, if you know how contact cement works, you let it dry, at least until it's shiny, and then I attach the vinyl to the wood frame on the edge at one side. Then I go straight across to the other side of the frame, pull the vinyl snug, not tight, but just snug. You don't want it real tight. And then lift it up and attach the contact cement at that point. And then I do the same thing on the other two sides. So at that point, I have a taut vinyl membrane that is pulled taut like a cross, like an X. Then I start working on the corners with the contact cement and attaching it. Normally you get a pretty good, nice, tight surface. You don't want it too tight because you don't want it pulling on the frame. Over time it can actually deform the frame from the tension. Now this is a diffuser without any particular spacer. So even at this angle you can see the effect that the diffuser has on the cones of emission. Now remember, I explained earlier the cone of emission that I'm talking about is from the LED device, not from the individual atoms in the semiconductor material. You can see here that the center of those cones in the diffuser bright enough where the camera CCD is again saturated and looks white. If you were looking at this with your eye, you would see magenta spots. Remember, we've been talking about light planes, round light planes, spots. So this is where we're headed. I added a 2.5-inch spacer between the LED strip and the aperture diffuser, and this increases the diffusion effect. And you can see that there's a big difference between this and what we had before. 2.5 inches, you can see that's just a 1 by 3. Now those of you that are not familiar with dimensional lumber, when they say 2 by 4, 2 by 6, 1 by 3, 1 by 6, 1 by 2, that specifies the dimensions of the rough cut lumber from the sawmill, not the planed finished lumber that you see here. So typically the 1 inch portion of the dimension is really 3/4 of an inch. A 2 by 4, the 2 inch end is actually 1.5 inches, 1 5/8. And the 4 inch is about 3.5 inches. This is a 1 by 3, but it's really 3/4 of an inch by 2.5 inches. When you go to working with dimensional lumber, make sure you take your tape measure and measure things before you just think, well, it's a 1 by 3, therefore it's 1 inch by 3 inches. It's not. Comparing the previous slide that had no diffuser space other than about 3/4 of an inch the thickness of the aperture frame to the LEDs, we've added 2.5 inches, so technically we have 3.25 inches. And that's actually, at this point, excellent diffusion. You just see a very nice, even diffusion of magenta going across that aperture diffuser. Now keep in mind that we have a light shining on this, or maybe that was a flash from my camera, I don't remember. That's kind of fighting this image. If you were to see this in a darkened room or low lighting, it looks a lot more intense. From this point, we bumped up the diffuser space. So the spacer is 5.5 inches plus the frame. It's a 1 by 6, which is 5.5 inches, then add 3/4 of an inch. So this is 6.25 inches spacing between the LED strip and the membrane that's your primary diffuser. Technically, if the white box wasn't there, this would be the diffuser. But because the white box is there, the white hole, it's also doing some diffusion because, and I'll say this more than once, the LEDs that you look at now are obviously illuminating the back side of that film, that vinyl sheet. Some of that light is reflected back into the box. Some of it is transmitted out and diffused. So the light that is reflected off the back of the membrane reflects back against the flat white paint, is diffused some more, and then comes back out and hits the membrane again. If you look at the far extremes of that aperture diffuser, it looks pretty even lighting all the way. I mean, you got the bright stripe there, but if you move up and away from the camera, you see that it's a very nice even diffusion. You definitely cannot see any image coming through from the box. As a matter of fact, flat white is such a good diffuser that it's hard to even see the seam where the back, the 3/8 plywood meets the sidewall of the 1 by 6. You can see the seam there. And I made no attempt to clean up that seam. I just set this 1 by 6 frame right on top of the plywood. As a matter of fact, there's a little space there because the LED strip extends underneath of it at one point. At this point, you should be flashing back on some of the previous slides like this one. Now I'm showing you all 3 steps here. Just the diffuser, aperture diffuser, then with 2.5 inches added, then with 5.5 inches added. I started to say that you should be flashing back to some of the previous slides like this one. So if you look at the upper inset there, you see what look like white dots, but they're really magenta. It's just the camera has decided that they're white, but they're really magenta circles. Here you had LEDs on the bottom, the little dots, as you look directly at them. And then right above them is a side view. The 3 dots on the bottom, you wouldn't see those and these other 2 images simultaneously. Okay, so we have 3 different situations here. The bottom one is you looking directly at the LEDs. The one in the middle is a side view or a top view of the LEDs and the cone of emission from the device. And then we threw in a dashed line to represent a surface. And then if you were to stand behind the LEDs, looking at that surface, you would see the 3 upper circles. They represent the spots or the light planes where the LED cones of emission are striking the surface. So the vinyl film acts as a diffuser So it's direct light here, and then it diffuses when it goes through the vinyl film. And then we move the surface further away. We move the vinyl film aperture diffuser further away from the LEDs. So you could say that this was the 2.5, 3-inch space, and this is the 5.5, 6-inch space. So we get bigger spots. The LEDs that I tend to use, the devices, have all three of them in one tiny little device. So the cones aren't separated. They pretty much, the cone of emission from each of the three LEDs tend to hit the exact same spot on the diffuser. They're not separated like this. But I just want to kind of refresh your memory of what we're looking at here when we look at the spots on the aperture diffusers. And then if we move even further away, they start to overlap and give you the primary colors here. Red and green give you yellow, green and blue give you cyan, and red and blue give you magenta. Okay, so now we're talking about the red, green, blue distribution. Now this is one strip, and this is was the top one in that slide we showed you a while back, where each device is one color, red, green, blue. There's red, green, blue, red, green, blue, red, green, blue, and it alternates like that for the whole 5-meter strip. Now, this is the edge of the aperture diffuser that you see here. That black with the texture, that's Gorilla Tape. What you're looking at is the direct light from the LEDs, but then if you go under the vinyl, that's what that looks like when it hits the back of the diffuser, when it comes out the front. See, it's well diffused, but not completely. Because the point of origin of each color is separated by roughly, not quite an inch, but close to it, when you look over there on the vinyl, you can see the red, green, blue areas. If you look real gently, I know that it sounds a weird way to say it, but if you look gently between the red, the green, and the blues, you'll see the cyan, the yellow, and the magenta. You don't see a lot of it, but I can definitely see some yellow in there. So here you've got blue, green, and red. Over here you've got blue, green, and red. The difference is one's direct and the other's diffuse. And if you look closely, you can see the cyan, the yellow, and the magenta. Now, once I threw in these call-outs, it became more difficult to see those secondary colors. But they're there. If you just kind of roll your eyes around a little bit on the image, you can pick out the yellow, the magenta, and the cyan. The point here is, with this type of an LED strip, you don't get real good diffusion or mixing. You get good diffusion, but you need to do more than just diffuse the light from the LED. You need to mix the three colors together to get the result that you want. However, referring to earlier slides, when the three LEDs are all mounted into one device, there is little or no separation of their cones of emission. When you illuminate the same area with red, green, or blue, they completely mix the colors. You start getting your combinations of yellow, cyan, and magenta, and all three together, and you have white. However, this is very difficult to do with the type of RGB LED strip where each device is one color. You need the strips where each device has all three colors. Red and green do not give you red, green, and orange where they overlap just orange. In other words, if the origins are separated by an inch, you're going to see red, green, and then you're going to see orange in the middle or yellow in the middle where they overlap. With the 50/50 RGB LEDs, which are one device with three LEDs mounted almost in the exact same spot, so the origin of the cones of emission are only thousandths of an inch apart, this is what you get from red and green. You just get a spot that is the combination of the two wavelengths. Now we have the 50/50 RGB strip. Now notice that every single LED is the same color. And it literally is, all of them are red because red's all we have turned on. Now here's another perfect example of overdriving the CCD in the camera. If you look at where the cones of emission intersect the aperture diffuser, in other words, on the left you see the red from the little LED devices, but then on the right you see what it looks like after it's passed through the aperture diffuser. You see that it looks yellowish and then white. If you were looking at this with your eye and not the camera, this is not what it would look like. But this is what we have to work with in the presentation for slides. Can't be helped. Okay, so that's 3/4 inch propagation space. If you want to call it 3/4 inch diffusion, because it's the distance of separation from the LED devices to the membrane, to the film, to the aperture diffuser that determine how good the diffusion is. So this is 3/4 inches. Because the diffusion is not that good, in other words, the individual spots are still noticeable, this means you could definitely add more distance between the LED devices and the aperture diffuser. Now here we bumped it up to roughly 3¼ inches, and you see it's much better. But you still see the yellowish in there. The yellow's really not there. That's an issue with the camera charge coupled device. But you see that is better. Okay, and if we compare it to the previous, you can see it's much better. Now let's jump up a greater space, and you can see now you have really good diffusion. Now this is 9 inches. Most people can't afford to give up 9 inches of space out from the wall to mount their light planes. So 9 inches deep is a luxury. There's another issue with construction as well that we'll address later. This provided a total of 9 inches of space between the LED devices and the diffuser membrane. Big difference. The distance, as I said, is a luxury if you can afford the space on your wall. And the extra work to reinforce the sides of the spacer or the sides of the white hole to prevent bowing and twisting with humidity cycles. If you took two 1x6s and mounted them parallel to each other, like you would have here, and then stretch something tight across them, in the beginning it would stay tight. But as you go through humidity cycles, in other words, the building gets humid, then it dries out, weather changes, seasons change, the boards tend to warp under the pressure, and then the vinyl is going to sag. So you would have, if you're going to have long spans and boxes this deep, you're going to have to add some gussets in between the LED strips to keep the sides vertical. But that's not our subject for right now. This is what it looked like at 3 inches. This is what it looked like at, oh wait a minute. That's the 3/4 inch space. This is the 3 inch space. And now you can compare the progression as you move the aperture diffuser out. At this point, you should pause the video and make a list of the individually observable effects in this next photo. Okay, so this is the entire structure that we're using. So there are 3 primary areas here that you can look at. You can see the LEDs, the devices, they're tie wrapped to a yardstick that's laying at the bottom of that white hole, and it extends out underneath of it because it's 3 foot long and the box is only 2 foot. You see we have slid the aperture diffuser over to the right to expose the LEDs in the bottom of the white hole. But where it extends out over the box, the LEDs down below are still illuminating the back of that aperture diffuser. You should pause here and look this whole image over and see what you could come up with to comment on regarding this image. Let's assume that you pause and now you're back. Probably the most obvious is the difference between the aperture that is over the matte white, that would be the section in the middle, and that is over the black space. If we mark the boundary, okay, this is the area that we're going to look at right here. If we mark the boundary of the area illuminated by the centers of the cones of emission from the LEDs, you can follow the differences between no diffuser on the left through the diffuser with a white hole behind it, and then the diffuser without the white hole behind it. If we move the boundaries out to the next major drop in illumination, you can see it more markedly without the white hole than with the white hole. I mean, look above that top dashed white line between the area of the aperture diffuser that's over the white box and the area that's out on the side there over, we'll call it black space. Now you can see in the background it's not totally black back there, but it is dark. That's a big difference. Always ask yourself why when you have the opportunity to observe any physical behavior. Ask yourself the why. Why does it look like that? Each little tidbit of information like this is another tool at your disposal for the future. If you move the boundaries again out to the drop-off of illumination outside the white hole, you can really see the difference between inside the white hole and outside the white hole. If you concentrate on just these two areas, diffuser, what can you say about the two swatches of light? The one on the left is outside of the major cone of emission from the LED. The one on the right is also outside the major cone of emission from the LED devices. The difference between the two is the influence of the white hole on the actual light that reaches the back of the diffuser. And if you look at just those two squares, those two swatches, that's how much difference it makes having the white hole behind the aperture diffuser. In other words, to capture any reflected light and keep bouncing around until most of it finds its way out the front. Now there are actually some effects that you might want from the square or the swatch on the right, where you want strips of LEDs in the box, but you don't want them all bouncing around inside the box and finding their way out. You want a little separation because you want to create bands or stripes of color. That's a different consideration. Right now we're just dealing with simple LED light planes. So this does illustrate, these two squares illustrate how much light is lost from the LED devices when you do not have them captured in a white hole. Not a reflective hole, but a reflective diffuse hole. If this hole or box were lined with mirrors like aluminum foil, you would not get the same image. You would get multiple remnants of the original image, but it would not look like this. You want as much diffusion as you can get. So technically this is a two-stage diffuser, if you like. The aperture diffuser, the vinyl film, that's your primary diffuser. But you have secondary diffusion, which is surface diffusion, the white paint in the box that is further diffusing the light and reflecting it back to the backside of the aperture diffuser. So you can honestly say the matte white finish inside the white hole is one diffuser and the vinyl film is another. So you have two diffusers here. Again, if you compare these two areas, another little tidbit aside, if you were inside of the white hole, looking at the inside surface of the aperture diffuser, the vinyl film, in other words, if you were on the other side of it from where you are right now, you would see that it is illuminated with red light. In other words, the red LEDs are illuminating the backside of that film. Some of the light is reflected back into the white hole. That's what you see bouncing around. And you can see red light everywhere in that box except where there's a little shadow because the yardstick is under the side of that box. In other words, we don't have the strip actually mounted on the back plate. It's just a yardstick laying there, and so it created a little gap. If that wasn't there, you would be hard-pressed to see that seam. And then there's another little seam you see where we've set the 1x6 on top of the 1x3, and it's not sitting on there perfect. Observe what you can. Another difference is the sharpness of the strongest illumination at the center of the cones of emission outside the white hole. So if you compare the most intense area of illumination at the aperture diffuser that's over the white hole and then move to the right where it doesn't have the white hole behind it, you can see that it drops off much quickly. I mean, it drops completely off to black at some point. But you can see that you have a much more intense It's a sharper contrast between outside the white box and over the white box. Last but not least, the inside edges of the diffuser frame that extend outside of the white hole. If you look at the edge of the diffuser there, where do you think that light's coming from? You see, that's a 1x2 frame. So there's a 3/4 inch strip of wood there that's illuminated. Now it's kind of fuzzy because remember, you're looking at the light reflected off of it that is then coming through the film, coming through the diffuser. So it's a strip of light that's diffused. Where is that light coming from? Well, it's coming from the LEDs right below it, which means that the light emitted from those LEDs has quite a broad angle. But the light that you're seeing on that frame edge is scattered light from the LED because of impurities and the low efficiency of the epoxy case. Remember in an earlier slide we showed you the epoxy lens case. So that's how broad the light goes out from the LED. If you look at the other end of the LED strip, the one that you can see in the bottom of the box, you can see the yardstick, the tie wrap. If you go all the way over to the last LED, you can see some of the cone pattern on the side of that box. You see a real bright spot, but if you look a little above and a little below, you can see where suddenly the light drops off. That's kind of the edge of the intended cone of emission from those LEDs, but it's still pretty broad. I mean, after all, you want people to be able to see these LEDs from a lot of angles. In this case, we want a nice broad cone of emission so we get real good diffusion. Well, that's about 30 minutes or so. So we're going to stop right here, conclude this first section of part 3, an introduction to LED strips, and we'll pick it up right where we left off. Thank you.